Hi everyone, in this tutorial I'm going to talk a little bit more about mass spectrometry, in particular about a process called high resolution mass spectrometry that can be a little bit more useful than the stuff we looked at in the last tutorial. I'm also going to remind you about how to calculate the empirical formula of a compound, and we'll look at using the empirical formula and the molecular mass to find the molecular formula of the compound. So if you can make sure that you've got your class notebooks ready and your pens, you can make some notes as we go through, and I'd like you to bring your tutorial notes to your next lesson with you, please. So let's start with a very basic example of how you could use mass spectrometry and the molecular mass that you get from your spectrum to find the formula of a compound. So in this example, we know that whatever has been put into the mass spectrometer is a cycloalkane, and we know from the spectrum that its molecular mass is 42. So very basic. What is the formula of the compound? So we've got the elements here and the relative atomic masses. Obviously you would get these from the periodic table anyway. Now I know that for a cycloalkane it has the same general formula as an alkene, so we're looking for something with the formula CnH2n, so twice as many hydrogens as carbons. Now if we look at the relative atomic mass of carbon, we've got 12. So let's start with considering cyclopentane. Cyclopentane would have 5 lots of carbon in it. That would give us a molecular mass straight away of at least 60. That's without the hydrogens added on, which is too high. So cyclobutane would give us 48, again, too high. So let's go for cyclopropane, which would give us 36, and then we need to add on some hydrogens, and then we'll check that it comes to 42. So according to the general formula, for cyclopropane, if we've got 3 carbons, we have twice as many, 6 hydrogens. So 36 plus the 6 for the hydrogens would give us a molecular mass of 42, which matches with the question, so C3H6, cyclopropane. That's what's been put into the mass spectrometer. Nice and easy. So now we're going to have a little look at some issues that you might get trying to find a formula from a mass spectrum. So here's another similar example. This time I don't know what type of compound it is. All I know from this one is that we have a molecular mass of 78. Now the issue here is there are a lot of compounds with a molecular mass of 78. So here are a few: C2H6O3 weighs 78, C3H7Cl, where chlorine is the 35 isotope, weighs 78, C5H4n and C6H6 are some examples of compounds that weigh 78. So based on the molecular mass alone, in this case, we would not be able to figure out what the formula of the compound would be. So this is where the slightly better process of high resolution mass spectrometry comes in. So if we were to take a sample of the same compound and put it through high res mass spec, this is a process where we find a more precise molecular mass, so we have to start looking at the precise relative atomic masses, which we've got down here in the table. So in this case, the molecular mass of the compound is found to be 78.0468. Now, because we're looking at the very precise relative atomic masses, we find that actually those compounds that I mentioned in the previous slide, they will have different precise molecular masses. So going back to the examples that we had before, C2H6O3, if we use the relative atomic masses that we've got in this slide, the more precise versions, we find that the precise molecular mass for this compound is 78.0317. For C3H7Cl, the molecular mass for that one is 78.0236. So now they're starting to look a little bit different. C5H4n has a molecular mass of 78.0062, and C6H6 has a molecular mass of 78.0470. So now looking at these new precise relative molecular masses, we see that the best fit for the mass in the question, 78.0468, is this one. It's just been rounded up slightly to 78.0470, so the molecular formula must be C6H6. So high-res mass spectrometry is used when you could not figure out what the molecular formula of a compound is because so many of them have the same molecular mass. So now we'll have a little look at how this might look in an exam paper. Okay, so a scientist used mass spectrometry to analyse a sample of the air near a fertiliser factory. The sample of air included traces of a gas which was shown by its molecular ion to have a precise MR of 44.00105. Part A, state the meaning of the term molecular ion. Just a definition question, you just need to learn them. So the molecular ion is the molecule, the one that was put in to begin with, and you have to use the word molecule, with an electron removed. So the molecular ion is M+, as you would get in electron impact ionisation. Okay, so part B, use the following data to show that the trace gas was dinitrogen oxide, N2O, and show your working. So you are given the precise relative atomic masses of carbon, nitrogen and oxygen, and the key word here is show your working. So for this one, they've already given you the answer. They've told you it's N2O. You just need to show and prove that it is N2O. So you need to take 2 lots of nitrogen 14.00307 and add it to 1 lot of oxygen, which 15.999491. Then just show the answer, and the answer is, as it says in the question, 44.00105. So you would need all of that working out to gain the marks for the answer because you've got the word show up here. Okay, the next part, propane is used as a fuel in the fertiliser factory. State why both propane and its combustion product carbon dioxide might have been identified as the trace gas if the scientist had used relative molecular masses calculated to only 1 decimal place. So this question is highlighting the importance of high-res mass spec compared with standard mass spec and showing why we use it. So similar to what we've just done previously. So for this one, you could probably guess without even calculating it that the answer is that both propane and carbon dioxide have a mass of 44.0 when we do the calculation to 1 decimal place. So propane and carbon dioxide have an imprecise MR of 44, you could say, as does dinitrogen oxide. So finally, state why the precise relative atomic mass for the carbon-12 isotope is exactly 12.00000. Well, if you remember your definition for relative atomic mass, the relative atomic mass of any element is its mass compared with the mass of an atom of carbon-12. So scientists had to come up with a standard. Hydrogen would have been nice because it weighs 1. If we'd have said hydrogen always weighs 1 and we compare everything else to hydrogen, that would have made everything very simple. But hydrogen being a gas and not being quite as common as carbon got replaced by carbon. So it's just by definition. Or you could also say that it's the standard or it's the reference. That's fine. But the reason it has 12.0 is simply that scientists have decided that we're going to call it 12.0 and everything else will be relative to it. So that is high-res mass spec. That's all there is to it pretty much. It's just more precise relative atomic masses and more precise molecular masses coming out of spectrum. So we're now going to have a little look at empirical formula. So hopefully you remember the empirical formula of a compound gives the simplest whole number ratio of the atoms in that compound. So it just simplifies down how many carbons to hydrogens to oxygens to whatever else you've got in there. So if we just have a look at some examples, we've got this ester first of all with the molecular formula C6H12O2. So the empirical formula for this, if you could simplify the ratio down, we've got 6 to 12 to 2. Obviously all of those numbers can be divided by 2. So you'd have C3H6O. That's the simplest ratio. For every 3 carbons in that compound, there are 6 hydrogens and 1 oxygen. So that's the empirical formula. Okay, if we have a look at the alkene next, we've got a molecular formula of C4H8. So again, if we look at that formula, simplest ratio, for every 1 carbon, you've got twice as many hydrogens. So CH2, we can divide both of those numbers in the molecular formula by 4 to get CH2, which is the empirical formula. Okay, now if we have a little look at the one at the bottom, we've got an alcohol. This has the molecular formula C2H6O. Now sometimes, just to be aware, if you can't divide all of those numbers of different elements by a certain number to get a simpler ratio, then you already have the empirical formula. So as we've only got 1 oxygen in this compound, we can't make that any simpler. So this is the empirical formula, and it also happens to be the molecular formula for ethanol. Okay, and finally we've got cycloalkane, cyclohexane, which has the molecular formula C6H12. Now, if we simplify that, both of those numbers in that molecular formula can be divided by 6. So the simplest whole number ratio is CH2, which is the same as the molecular formula that we had here for the alkene. So just be aware that you can have the same empirical formula, but you've got a different molecular formula for different compounds. So an empirical formula won't obviously straight away tell you what your molecular formula is, so there's not enough information there. Okay, so here's an example of a question involving empirical formula. It's a little bit different than some of the ones that you might find, because you're already given the empirical formula. In this case, usually you would have to calculate it yourself. So we are told that for a compound, its empirical formula is C3H5O2, and by mass spectrometry, its molecular mass is found to be 146. So we need to find the relative formula mass of the compound, given its empirical formula and its molecular mass. So the first thing to do would be to work out its empirical mass. So if this were to be its molecular formula, what would its molecular mass be? So we've got 3 times 12 for the carbons, plus 5, which are your hydrogens, plus 2 lots of 16 for your oxygens. And if you calculate that, it comes out at weighing 73. So now you just need to know how many lots of the empirical formula are in the compound that weighs 146. So 146 is the molecular mass, divided by the empirical mass, 73, you get an answer of 2. So the molecular mass is twice the empirical mass, so the molecular formula will be twice the empirical formula. So our empirical formula was C3H5O2, so we need to double that because the molecular formula weighs twice as much, so it's C6H10O4. That is the molecular formula of the compound. So I'm whizzing through this a little bit. If you need to stop and go back and have a little look at how I've done that, just make sure you can get your head around it, that's absolutely fine. And we'll now move on to a question where you do have to calculate the empirical formula yourself. Okay, so here we've got an unknown compound which is found to contain 50.05% sulfur and 49.95% oxygen by mass. So you should be able to use percent by mass to calculate empirical formula, and then to go on and calculate molecular formula if you're given molecular mass, which is what this question's asking you to do. So the steps for calculating empirical formula from percent by mass are to, first of all, for each element, so sulfur and oxygen, you divide the percent by mass, so that's 50.05 on this case, and 49.95 for oxygen. You divide those percent by mass by the relative atomic mass of those elements. So sulfur weighs 32.066 if you want to be quite precise, and oxygen's mass is 16.00 grams per mole. Once you calculate those, the percent by mass divided by the relative atomic mass, you get a number of moles. So you get a mole ratio. So for sulfur, you get 1.5608. And for oxygen, you get 3.1212. Okay, so we've got a ratio now. The sulfur to oxygen ratio is 1.5608 to 3.1212, which isn't particularly helpful for writing a formula. So now we need to get it into whole number ratio, which will give us the empirical formula. So out of the two numbers that we've just calculated, you now need to divide by the smallest one. So for the smallest one out of these two is the one for sulphur, so we're going to divide by the number we've just calculated for sulphur, which is 1.5608. We divide that one also by 1.5608, and our answers are, for sulphur we get an answer of 1, obviously because we've divided one number by itself, and for oxygen we get 2, so the ratio is 1 to 2. So our empirical formula is 1 lot of sulphur and 2 lots of oxygen. That is the empirical formula. So just to remind you, for each element you take its percent by mass, you divide it by its relative atomic mass, and then out of all of the answers that you've calculated, you divide all answers by the smallest number that you got. Then you get a whole number ratio, write it as a formula. Done. Okay, so for the second part we're now going to work out the molecular formula rather than just the empirical formula. The molecular mass of this compound is 64.07. What is the molecular formula? So just like we did in the previous one, find out what the empirical mass would be. So for SO2 it would be the 32 plus 2 lots of 16, which would give you an answer of 64. And then similarly, as we did before, obviously you can see what the answer is, but 64.07, which is the empirical mass, divided by the molecular mass divided by 64, which is the empirical mass, give you close enough to 1. So 1 lot of the empirical formula is the same as the molecular formula, so the molecular formula is also SO2. Okay, so just put a quick recap on finding the empirical formula there for you. If you need to write down the steps, then pause here and take some notes from this slide, but it's just exactly what we've done on the previous slide. Okay, so we've got a multiple choice past exam question. Be careful with multiple choice questions, they are trickier than they look in a lot of cases. So the question says 2.40 grams of an explosive, J, contains 0.473 grams of nitrogen. J also contains 33.8% carbon and 1.41% hydrogen by mass. The remainder of J is oxygen. What is the empirical formula of J? Now, it's likely because I've read it out to you, you've noticed the change in units in the question. We go from working in grams to working in percentages, but you do need to be careful because I think reading this in silence in an exam, it's very difficult to get confused and to think that we're working in percentages for the whole thing. So the first step here would be to get it all into percentages. So we know the percent of carbon, we know the percentage of hydrogen, we can calculate the percentage of oxygen from what's left over, but nitrogen we've currently got in grams, so we need to work that out as a percentage. So of the 2.40 grams that we've got in total, 0.473 grams of that is nitrogen. So if we do that division, that will give us 0.197. And then if we multiply by 100 to get it into a percentage, we get 19.7% nitrogen. We know we've got 33.8% carbon, we know we've got 1.41% hydrogen, so if we take those two numbers away from 100, we will figure out the percentage of oxygen. So that comes out at 45.1% for oxygen. If we just jot down the other two as well, there we've got our 4 elements and their percentage composition in this compound. So again, we're going to divide each of them by their relative atomic masses. So I'm just going to use fairly imprecise relative atomic masses for now. We're going to divide that number by 1, we're going to divide that number by 14, that by 16, and that by 12. The relative atomic masses of hydrogen, nitrogen, oxygen and carbon. And the answers that we get are 1.41 for hydrogen and for nitrogen, and 2.82 for oxygen and for carbon. So the next step is to take the smallest of those numbers and divide all numbers by that. So our smallest is 1.41, so we'll divide that by 1.41, that by 1.41, that one by 1.41, and that one 0.41. Okay, calculate those. Quite simple, we've got one of those, two of those, and 2 of those, and that is our simplest whole number ratio for those elements. So now we simply need to write it as a formula. So carbon, we've got 2 of them, so we've got C2. Hydrogen, we've got 1 of them, so H. Nitrogen, we've also got 1 of them, so it's N. and oxygen, we've got 2 of them, so O2. So that there is the empirical formula for compound J. So the answer would be C. So that concludes my very, very quick run through of high resolution mass spectrometry using percentage by mass and calculating empirical formula. So now you just need to go back to the blog, click on the link for the post-tutorial quiz, and I would like you to complete that before next lesson, please, so that I can have a look at where you've gone wrong and we can talk about it in the lesson. Please bring your tutorial notes to lesson as well. Thank you.